Continuing our quest on this channel to eventually prove every single formula that ever appears in Maths A-Level, today we're taking a look at the formula for an infinite geometric series, which is one of the formulas given to you in the formula booklet. Just to be clear, what we're talking about is a situation where you have the common ratio of a geometric series being between 1 and minus 1, and if that's the case, the infinite geometric series can be given by the formula a over 1 minus r. Now it is worth noting that in theory for Maths A-Level you're meant to know off by heart the proof of the formula for the sum of the first n terms of a geometric series. That is a bit of a mouthful to say, but therefore it's worth noting that as a result I'm not including the usual warning for this series, and that's not because I'm expecting anybody to look at this proof and learn it off by heart, because you don't need to, but at the same time this is starting to get on the borderline, on the edge of something they could ask you in the exam, maybe as a part B or something like that. So therefore that's why I'm not giving the warning by saying, because I don't want to say you don't need to know this, but equally I wouldn't worry about going out your way to make sure you learn this either. It's basically just using skills you're meant to know, but, not knowing it off by heart, if you will. So there you go, that's something worth considering, but what do we need to know in order to be able to do this proof? Well, I'm expecting you to obviously have a general understanding of geometric sequences and series, because that's probably why you clicked on this video in the first place. And also, to be clear, what we're talking about when we say S infinity is we're talking about taking all the terms in a geometric sequence and adding them together forever. And a geometric sequence is defined as a sequence with an nth term of a lots of r to the power of n minus 1. Cool. And actually, I'm going to do this proof in two different ways. I know, amazing, right? And it's because I was originally only going to do it one way, but I thought, I know what's going to happen. Somebody is going to, in the comments, write, oh my goodness, I can't believe he proved it this way rather than proving it this other way, which is just so much easier. So therefore, I'm proving it both ways. So everyone will be happy. Hooray! And therefore, to do this first method we're going to use to prove it, we're going to make use of the formula for the sum of the first n terms of a geometric sequence, which of course is the formula Sn equals a lots of 1 minus r to the power of n, all divided by 1 minus r. To convert that into the formula for S infinity, we're therefore basically seeing what happens to the formula if you make n just become bigger and bigger and bigger forever, or if you want to write it in posh limit notation, the lim as n tends to infinity, if you will. But in order to do this, we need to consider 4 different cases. So to do that, we're looking at if r is bigger than 1 first. Then we'll look at the situation where r is less than or equal to minus 1. Then we'll look at the situation where r is equal to 1. And then finally, the nice case that we really care about, which is if r is between minus 1 and 1. So, starting off with r is bigger than 1. Now, if r is bigger than 1, that means every time we go from one term to the next in the sequence, we're multiplying by a number bigger than 1, because that's what the common ratio is, what we're multiplying by each time. So if r is bigger than 1, that means the terms in the sequence are getting bigger as we go along. But if you're adding all the terms in the sequence as you go along, and they're all getting bigger, then we already know, we don't need any posh formulas to tell us that we know the sum of that is going to approach infinity, or minus infinity if the first number was negative. So we already kind of know what the result is, just intuitively. It is worth noting, though, that interestingly, the formula does back this up, though, because if you take a number that's bigger than 1 and take it to a power that tends to infinity, then it's going to tend to infinity. So, therefore, if you plug that result into our formula for S infinity, then you're going to get, or rather Sn, then you're going to effectively get an answer infinity if a is bigger than 0. Because the top of the fraction will basically become negative infinity and the bottom will become some sort of negative number, and the negatives will cancel out to give you positive infinity. However, of course, if a was less than 0, then you'd get negative infinity instead, but either way, it's approaching an infinite value of some sort. Cool, that's the first case done. What happens if r is less than or equal to minus 1? Well, you see, at this point, the thing to be aware of is this stuff just starts getting weird, and therefore considering what the sum to infinity in this case is just doesn't make sense to do. Why? Well, if you take a look at the situation where r is equal to minus 1, the best case scenario you can have in this sort of situation, you have the first term, then take away the first term, then add the first term, then take away the first term. And if you do that forever, you're not going to get any defined results, not any set result, because it's just always going to be oscillating between being a or 0, depending on where you stop. But the problem is you're not stopping because you're doing it infinitely. So therefore, basically, the sum in this situation is just undefined. It's got no result. It diverges, in other words. And to illustrate this further, it's even worse if r is less than -1, because not only have you got this plus minus situation happening with the terms, because the common ratio is a negative number, they're also getting bigger as you go along. So therefore, the sum is getting bigger, but also at the same time fluctuating between being positive and negative. So therefore, this result still just doesn't make sense, basically. You can't even say it tends towards infinity, because you're not sure if it's tending towards infinity or negative infinity, because it's always changing. And so therefore, in this situation, there is no actual real result. This is where we'd say that r to the power of n would be diverging. And it's worth noting that actually tending towards infinity is an example of diverging, but that's still diverging to something, towards something, whereas this is sort of just not settling on any given result. Worth noting, therefore, though, that the formula does back this result up, though. The sum doesn't make sense, and the formula will tell you that it doesn't make sense, because r to the n, part of the formula, will just diverge, therefore telling you, basically, the sum is diverging as well. So therefore, that's worth pointing out, but basically, this case is silly. Let's move on to one that makes more sense after pointing out that this just diverges. So, if r is equal to 1, well, again, do we need to do any of this stuff? We already know that if r equals 1, all the terms in the sequence are the same as each other. So therefore, if you add just the same number to itself infinite times, you're just, of course, going to get infinity, or negative infinity if all the numbers were negative, and therefore we already know the result. Which is kind of good, because you don't want to use the formula in this case. If you plug r equals 1 into Sn, you're going to get something that's undefined. But if you're a further maths student, there is a way of actually trying to find out what this is using the formula. The formula does back up the result. You just got to use two limits. You could make the limit of r tending to 1 first, which you could evaluate using L'Hopital's rule if you know what that is, and go from there. So that's another way of approaching this. But either way, we already know what the result is. It's infinity if a is bigger than 0, or negative infinity if not. So therefore, moving on to the final case, which is if r is between 1 and -1. The nice case, finally. And the reason this one works so nicely is because if you take any number that's between 1 and -1, and you times it by itself, it ends up being smaller, or if I could say that more accurately, closer to 0 than it was before. So if you keep on multiplying by itself, it's just going to keep on getting closer and closer and closer to 0 until it eventually is 0. And that will happen because we're taking it to a power of that's approaching infinity, basically. So therefore, that's really nice because the formula for Sn backs this up. Because if you make n tend to infinity, r to the n is tending to 0. And therefore, if we include this as part of this result we're looking at before, then the numerator is just becoming a lots of 1 minus 0. Which just simplify to a over 1 minus r. And there you go. Amazing. We have proven the formula for S infinity. So that's one way of proving the formula very thoroughly by considering all the different cases and seeing how that affects Sn. However, the second way of proving it is to basically make use of a proof that probably some of you have seen already before for writing, I don't know if you've seen the proof for people rewriting a recurring decimal as a fraction. It's basically the same idea as that, but with algebra instead. And alternatively, another way of looking at it is very similar to the proof for the sum of the first n terms of a geometric sequence with just a couple of adjustments made to it. So, therefore, what we're talking about if you start off with S infinity, that is this expression here. We're adding all the terms in a geometric sequence together infinitely forever. And here's the sneaky thing. You could multiply this entire sequence by r. So r lots of S infinity will get ar plus ar squared plus ar cubed. And that's interesting because you'll notice there's a lot of similarities between what you're seeing in r lots of S infinity and S infinity. In fact, the only thing that's different between them is just that S infinity starts with an A, so it's got that extra thing almost, it appears. That's important because it means that if r is between -1 and 1, we can do S infinity take away r lots of S infinity. And if you do that, all the terms are going to be cancelling out with each other, except for that A that's in S infinity that's not in r lots of S infinity. Now, admittedly, some people are really unhappy with the idea of being able to do this, but there's a couple of reasons why we are allowed to do it. The first thing is to point out we are only allowed to do this because r is between 1 and minus 1. Because if it wasn't the case, then if r is, for instance, less than or equal to minus 1, we already know that's just a silly result, full stop. But if r is bigger than 1 or even equal to 1, then you're not allowed to do this because you'd be doing effective infinity take away infinity, and basically you're not allowed to do that sort of maths with infinity because it's weird. So therefore, because that's not happening, that's why we're allowed to do this. We've got a number take away another number that's finite. But the other way of looking at this, if that sort of explanation doesn't make you happy, is to be aware that even if what some people argue is they look at these two sequences, they go, okay, I know I can see that a would be left over, but r s infinity has got like that ar to a higher power than s infinity has. Well, technically not, because both of the terms are, or both the sequences, are going on forever. So eventually, all the terms will be appearing in both sequences. But even if that idea doesn't make you happy, because it doesn't make a lot of people happy, even if you want to consider the idea that r lots of s infinity, has an extra term that s infinity doesn't, and it doesn't, by the way, but if it did, it would be basically a number that's 0. Because as we said, if r is a number that's between 1 and minus 1, r to a really big power, as we already mentioned, would effectively approach 0. So even if you did include an extra term there, it would basically be saying we're adding an extra number of 0 on, or taking it away technically. But anyway, either way, this fact we've written here is true. All you got to do is factorize 1 minus r out of it, and then divide both sides by 1 minus r, and then boom! S infinity is equal to a over 1 minus r. Amazing! We've proven it! And so if you enjoyed this, please do check out some of the other videos on my channel. I've got loads of proof videos already on there, and there's loads more still to come, because as I said, I'm trying to prove everything in Maths A level. Enjoy! Subscribe to my channel!